doctor because he is a doctor.
Oh, doctor.
All right. So, you were explaining this bad faith actor.
Yeah. So let me just get his face on here. So this is the guy that we're responding to. This guy, he runs a YouTube channel, Sky
Hello.
Scholar, and it's this guy right here. Okay, so this is Dr. Pierre-Marie Robitaille. Now, I probably said that wrong, but yeah. And this is an individual who is extremely perplexing to me because it's not an unintelligent individual. It's not an unqualified person. It's somebody who should absolutely know better than what is coming out of their mouth, okay? He has a legitimate PhD in something. I don't know exactly what the PhD is in, but I know that he made really, really important advances. I can look it up really quick.
So it's not in like
I'll bet
scientism,
it's not
right?
astrophysics.
No, it's not astrophysics. It's not astrophysics. But he invented or developed a major advancement in MRI imaging.
Wow.
And like on Rational Wiki has a page on this guy, which I can probably just briefly show really quickly. So he's an accomplished radiologist, and he was a director of the MRI research at Ohio State University. He made major advances. He's somebody who, if he had been awarded the Nobel Prize in medicine and physiology, like that would make sense. And that's why they probably lead with he's a Nobel disease type crank, because guy totally lost it. He was, they asked him to resign in 2000 because he started advocating for these really crazy fringe astrophysical concepts. It's very puzzling. And here, so we're watching video something in the playlist. This playlist is about his take on the cosmic microwave background, and his basic hypothesis is that we're always just measuring the ocean. This makes no sense. This makes no sense on 8 different levels.
Stephanie, I'm so glad you're here.
Yeah.
I'm pulling up. I'm trying to find the shortest video with Alan Guth in there.
Right.
Hello, everyone, and welcome to Sky Scholar. Today, the series on the microwave background continues with the discussion of the results obtained by the FIRIS and DMR systems on the COBE satellite.
So the COBE satellite was launched in, when was it launched exactly? In the early 90s, I want to say. 89 to 93 is when it was operating, and it was there to measure this. So the cosmic microwave background, for anybody who doesn't know, just very briefly, the idea is that after the Big Bang, the universe was opaque for a long time, and then it became transparent. And at that time, it was basically more or less all in thermal equilibrium with itself. The various parts of the universe were, and when it became transparent, that light just kept propagating forever. That black body radiation light just kept propagating forever. And now we see it, and it follows a particular curve that says that basically the background temperature of the universe is around 2.73 Kelvin or so. And he's like, nuh-uh, basically.
So a little bit of background, more background. People started to notice that two radio astronomers, Penzias and Wilson, were working for Bell Labs, and at the time they had a great big huge microwave antenna in 1965. And Bell Labs was using microwaves to do telecommunications at the time, right? And they kept hearing this stupid hiss, and they couldn't figure out what the fuck it was coming from. They were driving them nuts. They were going pigeon shit wild. And literally, because pigeons would go into the thing looked like a great big horn, a huge horn of plenty, and the pigeons would go in there, take a dump, and so they figured it's gotta be the chicken shit. So they went in, cleaned the whole thing out of chicken shit, and still it was there. They couldn't figure out what it was. They finally figured out that it was this thing. It was this noise that they were hearing in the microwave area of the radio spectrum that was it was the same coming from every single direction.
Yeah.
And they got a Nobel Prize for figuring that out. So we'll see if this fellow gets a Nobel Prize for figuring out something.
If he is right and he proves and it's proven that he's right before he dies, he will win one, but he's not right. So this, by the way, is that microwave antenna that Stephanie was mentioning. That might be Penzias and Wilson. I'm not, but it's a giant thing that reflects a bunch of the microwave radiation into this thing, and then it hits basically another thing that then records it somewhere. It's a big metal.
And that's them.
Yeah. and it's pretty neat. And when they turned it on, yeah, there was just this background hiss, and they were like, what is this?
Exhaustive analysis of the COBE-FIRIS measurements in this paper, and I urge those who are interested to consult that resource. It is simply not possible to cover all the issues related to each satellite in a reasonably compact video series. I am trying to provide a solid overview, but for those interested in studying the details, you must move beyond the videos. In COBE, or radiological analysis, not only are details about the COBE satellite provided, but I also emphasize problems with rushing the instrument to launch and the ever-present concerns relative to water contamination in the microwave background measurements. COBE was launched in 1989 and positioned in polar orbit around the Earth at an elevation of about 900 kilometers. COBE has a heat shield, but this shield is designed to provide Earth's infrared radiation from affecting the instruments on the satellite. The shield has no ability to stop microwaves from diffracting into these instruments, including the all-important FIRIS horn.
Now, this right here is sort of his fundamental issue with the COBE satellite. So the COBE satellite goes up and it points a microwave horn like we just had on the screen, but it points one of those, and smaller, just out into space. Then you perform measurements. And his point is that it is going to be influenced by microwaves coming from the ocean and hitting this thing and bouncing around and into it.
Why would he think that?
Because I don't know. I don't know why he thinks that. That's what's so frustrating is he, not in this video, but I spent a lot of today watching videos of this guy, and he'll find quote after quote after quote of people being like, oh, by the way, like water vapor in the air, Penzias and Wilson, like when they were measuring it, water vapor in the air would make their reading go up, and they were like, oh, great, that means it's working because we know that it can be a source of noise. And yet, the people that he's appealing to be like, this is a source of noise, are also the people he's saying didn't account for this source of noise. Also, the source of noise fundamentally just wouldn't do what he's claiming it would do. And he's saying that this satellite, which is able to, because he thinks that this shield is going to prevent the IR radiation, but not the microwave radiation. That's like mostly silly. It's not totally silly because microwave radiation is at a lower wavelength, and it might behave in a near field way as opposed to a far field way, but it's really dumb.
Is it totally bullshit?
It's 99% bullshit. Yeah. And mostly what he's saying.
You got me on the field stuff, but clearly this man is outstanding in his field, so.
Yeah, that's the thing is he
just doesn't happen to be his field.
Yes, and I think that possibly it is slightly closer to my field than it is to his field, but it's not like crazy closer. Like nuclear magnetic resonance imaging has a lot of physics. It's not a lot. It's just nuclear physics, which is not radio astronomy. This is radio astronomy.
Mm-hmm.
FIRIS was famous for having obtained the...
FIRIS, by the way, stands for something absolute photospectrometer. And it's the thing that basically says, okay, when we point at this spot in the sky, we're measuring this whole spectrum. He's going to show a spectrum,
body radiation curve ever, as you can see in this figure.
So this is the data.
Hawking stated that this represented the discovery of the century, if not of all time. Indeed, the COBE authors are proud to claim that their measurements had such high signal-to-noise that one had to blow up the error bars by a factor of 400. That their measurements...
Yeah, this is data with a line of interpolation through it. With the fit line, the data points are on there. It's just that their error bars are so small that you can't see them. This is incredibly...
I think that one had to blow up the error bars by a factor of...
When you blow up the error bars 400 times, then you can see them. It's astonishingly pristine, beautiful data. And it looks exactly how you would expect it to look. And there is no comprehensible reason why you would get such a precise match to this particular shape if you were just looking at a parasitic signal from Earth's oceans. It makes no sense.
400 just to be able to visualize them. Now that is signal to noise. In fact, it is nearly unparalleled signal to noise for such measurements. But in this regard, I have a note of caution. Powerful signals employ proximal sources. Be careful to make cosmological claims based on signals measured near the Earth, especially when the possibility of diffraction has not been eliminated. In response, many are quick to highlight that the microwave background has also been measured by the WMAP and Planck satellites. Those satellites were positioned.
So this is what COBE produced. COBE produced a measurement at all of these different, at every point that has an error bar, it produced a measurement of the absolute magnetic intensity of the CMB. And it was in orbit around the planet. It was in a polar orbit. Like it had a lot of different Earth-like environments that it was sampling over. And noise subtraction, it is like the thing that they spend all their time doing, is understanding and accounting for the various sources of noise. Because when you look out into space, you'll have a lot of signals coming from our own galaxy and from Earth and from all sorts of things. Not so much the ocean, though.
In response, many are quick to highlight that the microwave background has also been measured by the WMAP and Planck satellites. Those satellites were positioned at the second Lagrangian point, as you can see here. This point is located about 1.5 million kilometers from Earth. Lagrangian points are locations in space where the orbital motion of the body and the gravitational forces perfectly balance each other.
So the James Webb Space Telescope is also in a Lagrange point somewhere. I don't know which one it is off the top of my head. COBE was the first like big CMB satellite. Then they sent out WMAP, which stands for something. I can't remember. Wide something, whatever. And then the Planck satellite, like a bit over a decade ago, was a more recent one. And those two did differential measurements. They didn't do an absolute measurement, and at least they weren't designed to produce an absolute measurement of as high accuracy. So they didn't publish one because that's not what the devices were designed to look for. And he doesn't seem to understand this.
As a result, any object placed at a Lagrange point will tend to...
Also, these are millions of miles away. Over 1 million miles away from Earth. They're way further than COBE, and yet all of their measurements are completely consistent with what COBE found.
hover about that location and stay fixed relative to the Earth. There are a total of 5 Lagrangian points. Located at L2, both WMAP and the Planck satellites were shielded from microwaves originating from the Sun or the Earth. Again, the satellites had a heat shield to guard against electromagnetic heating. However, neither of these two satellites ever measured the blackbody curve associated with the Furious Horn. They only...
Oh, he means that they didn't do a direct absolute measurement of each little point. So like in this plot that was down here, in steps of 0.5 millimeter at every wavelength, so 0.5 millimeter, 1 millimeter, 1.5 millimeters, so on up to like a bunch of millimeters, they measured the absolute intensity of the microwave hiss that you see. And these ones didn't do that. Instead, what they did was they had 2 channels that measured the hiss and at slightly different points in the sky and subtracted the 2. So you got a super, really nice measurement of the differential thing, but the absolute scale, for Planck, it was only designed to have an absolute accuracy of 0.5%, which is fine because that's not what it was trying to do. It was trying to say this part is brighter than this part by a part in 10 to the negative 4, even if we don't know what the absolute value is, to better than a part in 200. And that's fine.
If you like, I can share a comparison of CMB results from COBE, WMAP, and Planck.
Yeah, sure.
Yeah, if you have it. Okay, what are we looking at?
No, you go for it. You're the...
So what we're looking at here is on the left you have COBE, and COBE was designed to make an absolute measurement of the spectrum at all of those different points that we saw in that plot with those error bars. What WMAP and Planck were designed to do was we already measured the absolute black body spectrum very precisely. We can fit it out to like 4 decimal places, which for a thermal effect is crazy. I mean, thermometry is very rarely done to that level of precision. It's very difficult, and it's because the CMB came from an almost perfect black body. So what WMAP and Planck are doing is they're looking at 2 spots in the sky, and they're saying, okay, this spot is a little bit hotter than this spot. The microwaves that are coming from there are a little bit shifted over than the ones coming from over here, but very, 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 very small. Basically, COBE measured how heavy if we were measuring something else, say we're measuring this book, okay? COBE can measure exactly how many grams this book is to some part in a small number, like 1,000 or 10,000th or something like that. But it's sort of coarse graining over the whole sky. It has very poor resolution. WMAP and Planck, they don't know how heavy the book is, but they know this piece of paper, they can tell that this piece of paper is a little bit heavier than this piece of paper.
Wow.
It's a different measurement.
Okay.
It's a different measurement, but you have to get the thing roughly right. It's like using a balance instead of an absolute scale. A balance compares to another thing, and an absolute scale has to be calibrated to some absolute sort of.
Okay.
Measuring basically different temperatures. The really, really
tiny, apart in 10,000.
And what you're looking at, the reason for trying to refine that is because the CMB is reflecting the state of the universe at what, 200,000, 300,000 years after the Big Bang?
Something like that. The number I'm pulling out of my butt is 350,000 years after the Big Bang. It shows sort of the temperature anisotropies, the fluctuations in the temperature.
That and all of that eventually provides the framework for the structure of the universe.
Yes.
As we know it, because those
Yes.
little tiny differences in temperature, differences in energy is mass, and so these little clumps just sort of all come together, and we wind up with galaxies and stars.
Yeah.
And all that other stuff, and that's where it came from. It's pretty remarkable.
Yeah, it's super cool.
Acquired data linked to microwave anisotropy maps. Moreover, as you will learn soon, WMAP was a differential instrument, always taking differences between two channels. It subtracted the signal observed from one region of the sky from that being sampled in another region. As a result, it was incapable of obtaining the equivalent of the Fearus curve. As for the Planck instrument, it used pseudo-differential radiometers at low frequency. These should have been able to confirm the Kolbe-Fearus findings, but they never did. We will cover all of this in greater detail in later videos, but for the present, let us return to the Kolbe-Fearus results, as they represent the only black body measurements ever obtained from space. Now, as a point of interest, the results of the Kolbe-Fearus horn are often plotted in different ways.
And the reason for that is so basically, the Planck satellite measured the deviations from this line. Kolbe measured the line. Planck measured the deviations from the line. Fundamentally, you have to have the ability to measure the line at sort of some level in order to measure deviations from it. It's just that it's the example I gave with a scale. If you have two enormously heavy objects and one slightly heavier than the other, you can tell that even if you don't know exactly how heavy they are. The idea that the data would make any sort of sense if it wasn't on top of this line is comical to me.
And this can lead to some confusion for the novice. So let us go through this briefly. Most commonly, you will see the Kolbe-Fearus results plotted in wave numbers, as in this figure. A wave number is exactly what the name implies. The number of
I hate
waves
wave
per unit
numbers.
distance. Symbolically,
There are a lot of different units that you can give. You can do it in wavelength, you can do it in wave number, you can do it in wave frequency. And wave number is my least favorite because it's technically a frequency thing, but it feels more like a wavelength thing. Like, this plot has the same shape on a wavelength plot and a completely different shape on a frequency plot, even though this is ostensibly a frequency. It drives me crazy. And it's also measured in inverse centimeters, which I just don't like. Give me the actual wavelength. Don't give me the inverse of the wavelength.
It's expressed as nu bar and
is that what he's doing?
Yeah, but that's not his fault. That's fine. This is inverse centimeters are a very standard spectroscopic notation.
Okay.
It's just one that so I don't do spectroscopy in a classical sort of spectroscopic sense. I do spectroscopy all the time, but the x-axis of all of my plots for spectroscopy is always frequency. It's always like in megahertz or kilohertz or something. Kilohertz is a unit of frequency, and inverse centimeters is not a unit of frequency, even though it technically is, but it shouldn't be, and it bugs me.
Over the wavelength. This leads to a scale in reciprocal centimeters. Fearus data can also be plotted as a function of wavelength.
See? It looks exactly the same as the wavelength plot. And this one makes way more sense. This is the wavelength of the radiation. 1 millimeter wavelength means that the light, it has an electric field that goes up, and then down, and then back to 0. And that distance is 1 millimeter. Very straightforward.
It's millimeters, as you can see in this figure. Finally, the Fearus data can be plotted in terms of frequency, typically gigahertz.
These two plots are showing exactly the same data. They're just different units.
All these plots can have differing y-axes. Typically, one will display intensity, with units involving either joules or ergs. So do not let all these depictions bother you. They are all representing the same thing, namely a black body spectrum with an apparent temperature of 2.725 Kelvin.
So I want to give Dr. Robitaille credit here. By the way, I'm not saying that sarcastically. I'm of the opinion that if somebody earned their PhD legitimately, until and unless you can, and this might be self-serving, until and unless you can show that they didn't earn the degree legitimately, even if they completely screw up and are a terrible scientist later, if you forget how to read, you don't lose your high school diploma, right? Same kind of logic. So I'm not being sarcastic when I refer to him as doctor. I will never refer to him as a physicist, though.
Isn't Kent Hovind a doctor?
Oh, no. See, Kent Hovind did not earn a... Are you trying to give me a stroke, Maya? Kent Hovind did not earn a PhD.
No, yeah, Deffer's been over his PhD many times. Or, I don't know, his, kindergarten science project.
Yeah, if I ever call If I ever call Kent Hovind a doctor, I'm absolutely being sarcastic, which is why I wanted to point this out here. Also, I want to give Dr. Robitaille credit. Everything he said in the last minute and 30 seconds, roughly, has been correct and pretty well stated, honestly.
Okay.
Also referred to as the monopole of the microwave background.
So does he have a problem with any of this, or is he just trying to
not the stuff that he just said in the last? So from here, he has a problem with this, but he doesn't have a problem with this, or he's about to explain his problem.
2.5 Kelvin. Now, the Fear's curve is also referred to as the monopole of the microwave background. That is often confusing for people, especially for those who understand that magnetic monopoles do not exist.
Yeah,
but in this case, the term is not associated with magnetism at all. It is related to imaging. Scientific images can be expressed in terms of spherical harmonics. A monopole is an image component that has the same value everywhere on the image. Here is what the monopole looks like for one of the frequencies of the microwave background using moleweed projection.
Basically, the idea is that you're going to have a part that is flat, and then you're going to have a part that fluctuates with some wavelength, and then another part that maybe fluctuates with another wavelength. And if you add all those wavelengths together, you can get any sort of curve you want, and you can do this with a three-dimensional view. It's what Fourier analysis is. It's converting from frequency into time or spatial structure. And CMB measured this, but the other satellites didn't, because that's not what they were designed to do.
Such projections are often used to represent the celestial sphere in 2D. They trade off accuracy in angle and shape for accuracy in area. Now, it is possible, of course, to present monopole maps for each frequency in the Fourier spectrum. They would all look the same, but differ only in intensity, which is represented by a different color. In any event, the Fourier horn was set to sample the sky over a phenomenal range from 3 to 3,000 gigahertz, or 1 to 95 reciprocal centimeters. The key point here is that still to this day, scientists have never been able to build a microwave detector which is sensitive over such a great frequency range. It is a physical impossibility.
So I found that perplexing, because it sounds like he just said they built this device that is able to measure over this range, and also it's impossible today to build a device that's able to measure over that range. He's not wrong, but he said it in about the most confusing way that you could. Because the thing is, these satellites have multiple detectors that are sensitive to different sub-ranges within that thing. You don't use the same camera to take a picture of an X-ray as you do to take a picture with your cell phone as you do to take a picture of a heat spectrum like a snake or something would see. I don't know if snakes actually see heat, but so I don't know why he's pointing that out. It's just a completely unnecessary thing to go on to.
It stands to reason, therefore, that the performance of this horn was never properly documented on Earth over this range of frequencies prior to launch. I have also highlighted in this...
So what he just said there was they didn't test it.
Sounds sus to me. NASA spent millions of dollars to send something up into the space, into the heavens, to kiss the face of God, and didn't test the fucking thing. I mean, yeah. Sure, sounds right.
Yeah, no, he says they didn't test it. The whole thing operating together as it operates in space, you can't test because you can't get rid of gravity, and you can't make a vacuum chamber in a zero-G environment like that big. You can test so many details of these subsystems that the thing he's complaining about, they totally tested it. It stands to reason they didn't properly calibrate. What are you talking about, bro? This is like if he turned on one of his MRIs and somebody said, it stands to reason that because you don't have a little guy with a camera inside each individual cell, that the image that you're reproducing is not accurate. It's actually, I think, a pretty good comparison at a high level, and it's why I'm astonished that this guy doesn't understand these things.
Is he working for like a
I don't know what he
think
does
tank,
now.
or is he's just really like being this daft over the internet?
Yeah, I think he's just being this daft over the, like, he has videos on the Thunderbolt Project YouTube, which was another pseudoscience BS thing that Professor Dave responded.
That the Fourier horn had a smooth interior and was therefore completely unable to prevent diffracted signals from being measured.
That's dumb.
In order to prevent diffraction into a microwave horn, the edges must be specifically designed with ridges. However, that will render the horn sensitive only to a narrow band of frequencies.
All right, I just want to point out here how rude Bree is being.
Which is not what the Fourier team wanted. But what is more concerning is the apparent rejection of low-frequency data. Remember that the CMB Fourier horn was supposed to be sensitive from 1 to 95 reciprocal centimeters. In fact, that is what was reported in the very first data disclosure in January 1990, as you can see here. But eventually, all data plotted for the region between 1 and 2 reciprocal centimeters is removed, as you can see in this figure. The reason that this is so concerning is that this involves a low-frequency end of the spectrum, that region most prone to the effects of diffraction, and also that region from which data should have been easiest to obtain.
That's an ignorant statement, I'm sure. Somebody not, I saw what Bree wrote.
What happened?
Apparently, in Bree's headcanon, she ships me and Professor Dave.
Oh.
anytime somebody who didn't work on the design and operation of an apparatus says this apparatus should be particularly good in this regime, they don't know what they're talking about compared to the people who do design and operate these things. Sometimes things you learn later that things have weird idiosyncrasies. And you realize later that the data in a certain part of the spectrum you can't trust as well because there are systematic errors that you can't account for. He's blaming these systematic errors, and then when they don't show that data, probably because there is some sort of error maybe. He contradicts himself, I feel like.
Fixin et al. Present a single sentence to explain the loss of data.
Also, this was 9 minutes of collection data, and it was presented at a conference. It's a totally different standard of rigor than what would be published in one of the most cited of all time astrophysical publications that won a Nobel Prize and is at the heart of like all of our cosmological data. You don't compare the two. This was 9 minutes of data. This is like a year of data.
However, the measured emission is higher than predicted, particularly at the lowest frequencies. Keep this in mind, as it shows that not all is quite right with the COBE-FIRIS data. As a result of all this, the FIRIS horn is not immune to detecting microwave signals originating from the oceans of the Earth. Beyond the FIRIS horn, the COBE satellite also had 6 differential microwave radiometers, or DMR, with 2 channels each, operating at 31.5, 53, and 90 gigahertz. Each of these pairs of radiometers measured the difference between 2 regions in the sky, separated by 60 degrees. It was from these instruments that COBE first reported the famous anisotropy map seen here. We will return soon to the anisotropy maps when we discuss the WMAP satellite.
I don't like this guy.
His arrogance is overwhelming, but a lot of these things come from some fundamental misunderstanding about the physics that's at play here, which this video goes he explores some of his own ignorance without meaning to.
So how does he derive a black body curve from the ocean?
I have no idea. The
data's there, right? I mean, the data's there. What does the effing ocean have to? You wouldn't be able to derive a black body curve from. You wouldn't be able to derive that data from. I don't. What's he getting?
So in this video he'll talk about how you need a lattice or something to cause a black body. That's not true. What you need is thermal equilibrium. I have a list of the things that you need. Okay, I prepared a list. You need like 4 things, according to what I was just randomly thinking, in order to derive Planck's black body law of radiation. And yeah, I pulled up, these are notes that I have from grad school where I went through in painstakingly detail, and I derived this in a way that I would write down so that when I had to figure it out again, I didn't have to figure it out again. I could just go to my notebook where I derived it in all of its detail and be like, yes, I understood every step of this at one point. Just because I can't do it at the drop of a hat now doesn't mean I didn't understand all of it.
But on that list, Dr. Tapioca, was there water there anywhere?
No, so water is on none of these items. None of these items is water. We have the Boltzmann factor. Basically, the probability that you're in a particular state is proportional to E to the negative thing of your energy. Energy conservation is the second thing. The fact that photons are not conserved, you could have any number of photons you want, and the fact that E equals h bar omega. This isn't Planck's law. This is I guess the quantization of. This is what Einstein won the Nobel Prize for, and he doesn't disagree with that. I don't think. I mean, who knows? But you don't need a lattice, which he's going to talk about how you need a lattice because the models that you use often talk about it. It's not really clear. He never actually makes a coherent point about why you need a lattice, in my opinion.
We now return to our analysis of the microwave background. For the time being, let us concentrate on the monopole, namely the blackbody spectrum, which we presented in the last video. I have often stated that in order to produce the blackbody spectrum associated with the microwave background, one must first have access to a vibrational lattice. As you can learn from this 2003 presentation, it takes more than a simple thermal equilibrium.
It does not. It only takes thermal equilibrium. I flashed through the derivation. It's not something that is particularly suitable for us to go through right now. It requires statistical mechanics and an understanding of the Boltzmann distribution, which is experimentally grounded. Boltzmann's constant is named after Boltzmann because he did a really, really hard experiment where he showed that the probability of an energy state depends on the energy.
A physical entity is required to generate the photons. Now, the vast majority of physicists will disagree with that statement. Most astronomers, for instance,
yes, we will,
believe that thermal equilibrium is enough, in large part because they have never thought about the problem.
You do. So he is very technically right in a certain extremely uncharitable reading of what physicists mean. Yeah, you do need some way for the photons to interact in some way with like their environment. You that isn't just reflecting. You do need to have absorption and emission.
But if you follow this channel, you are familiar with the extensive series of
here you go,
videos
Dad.
that I've released.
Here's a question. Here's an answer they could understand.
What are Dr. Microwave's qualifications?
Yes, apparently he's an actual doctor. Who knew?
I joined the Department of Radiology in 1989 at Ohio State? Yeah.
Yeah, Ohio State. Yeah, he worked at Ohio State from 89 to 2000 as a director of magnetic resonance imaging research, and he produced some really major good work in that field. And then he was asked to step down because he began to promote theories that were outside his realm of expertise.
Yeah, for example, I'm reading here, this is the Ohio State Department of Medicine.
They totally canceled him. What a bunch of libs.
Yeah.
Yeah, but I don't actually know what his either... I don't know. It's possible he's an MD, but MRI is pretty physics heavy.
Kirchhoff's law stands at the very heart of spectroscopic analysis, not only in medicine, but also in fields as seemingly remote as astronomy. Here we are. For me, revisiting Kirchhoff's law of thermal emission has resulted in questioning many established ideas in astronomy, including the origin of the microwave background, and most importantly, the nature of the sun itself. That is because the standard model of the sun relies on the validity of Kirchhoff's law in order to justify a gaseous state. Conversely, Kirchhoff's law is not valid, then the sun cannot be gaseous in nature. Along these lines, I have recently advanced 40 lines of evidence that the sun is comprised of condensed matter.
Specifically, I believe liquid metallic hydrogen.
Steph, the chat wants to know if you can turn it up, turn your microwave. Oh my God, your microphone up a little bit.
He thinks the sun is made out of liquid metallic hydrogen.
I thought maybe condensed milk is, but maybe not.
It's remarkably dumb.
To Kirchhoff's law and black body radiation.
Also, I want to say, so he has a video here called Stewart's Law. Like this is a thumbnail for a different video that he's advertising here. Stewart's Law, which he has quibbles with exactly the formulation of Kirchhoff's Law versus... I don't know if I pronounced that correctly, by the way. That's just how I was taught. Kirchhoff's Law versus this guy Stewart's Law, who I haven't said. It's kind of a pedantic issue that I don't think matters particularly much. But he spells it Stewart up here. And then here, we're in the section of Stewart's Law. If you look down at the progress bar, and it's spelled a different way. And I just noticed that. And I thought that was mildly funny.
Most physicists cannot even state Kirchhoff's law properly. They often confuse Planck's law with Kirchhoff, unable to see the tremendous distinction between the two. At times, they cite Stewart's law as Kirchhoff's law, not realizing that they are not the same. So before we go too far, let us make the subject clear. Stewart's law states that in thermal equilibrium, the emission of an object will be equal to its absorption. Of course, this is provided that no convection or conduction is operating. You can learn more about Stewart's law in this video.
It's pretty straightforward conservation of energy kind of stuff.
Stewart's law was derived from experiment. It is not simply deduced from theory. As for Kirchhoff's law, it extends much beyond Stewart's. It states that in the presence of temperature equilibrium, the radiation within any rigid opaque cavity will always be of the same nature. That radiation will be independent of the nature of the walls and depend only on temperature of observation and the frequency sampled. In other words, Kirchhoff advanced that blackbody radiation will be found in any rigid opaque cavity, provided that equilibrium is present.
Like I said, it's a bit of a quibble. I think he's wrong, but I think he's wrong in a way that, you can, if you go back to the original sources and you find the way that somebody originally formulated their law, it might be slightly different from how people tend to use it nowadays. I don't think that's technically correct. That's not really what it's about. It's more about
law this way, where
it's more about what goes in equals what comes out. That's really the core idea of what's going on here. Is what goes in is what comes out, and when it's not, actually there's a ratio thing, and it's this universal thing that depends only on the temperature, and that is true.
Wherein the emission observed from a small hole peering into a cavity is dependent only on temperature and frequency. Kirchhoff did not know
if you idealize the system. In a real system, there are going to be limitations to that statement, because, I mean, if something goes in and then it bounces off a little piece of reflective material and it comes right back out, that's not going to be the same spectrum as a black body. By the way, a black body is just a body that doesn't reflect. It only emits. So, yeah.
Functional form of the radiation, but he advanced that it would be independent of the nature of the walls. At the same time, Kirchhoff's argument was entirely theoretical. He had no experimental proof for what he was advancing. On this basis alone, his paper should have been rejected. Yet it eventually became a law of physics.
But it should have been. but it's a law of physics. But okay,
That's such a crackpot thing to say.
kinda.
I mean, it's like it has no theoretical, it has no experimental justification. Like, what do you mean? Yes, it does though. Like you can okay, and also Kirchhoff was before Planck, and Planck's law is the more robust version of it, and I've derived Planck's law, as I said. It's in the notebook. I don't understand where he gets this idea. Also, theoretical physics is still physics. Just saying.
One would think exactly. One would think that the theory says you do this and this should happen, and then you go out and you look and you do this, and by gum, that happens. Otherwise, the theory's the law ain't no law, right? You know.
Yep.
I don't get it really.
I heard theoretical physics being actual physics is fighting words.
There are contexts in which you can sort of. You can find people who will have that fight. 99% of the time, no. You're not going to have that fight. Theoretical physics is totally physics. Where people start to disagree, though, is if things like string theory are even theoretical physics. They are. It's also, all of it's a continuum. All of these things have different levels of rigor, of falsifiability, of domains of validity, of their usefulness for making concrete predictions for potentially doable experiments now versus potentially doable experiments in the future. Gravitational waves were predicted in some sense back in the 1910s, because in some sense the theory of general relativity predicts them, and the theory of general relativity had its sort of foundational stuff figured out before 1920, and yet they weren't discovered for all that time. Does that mean that Einstein wasn't doing physics? No, that's
it was literally 100 years on the dot, really. I mean, Einstein said Einstein said there are definitely gravitational waves out here that's implied by the nature of the theory, but we'll never see them.
Exactly.
And then the experimentalists figured out, hey, we can do this, and maybe we'll see them. And sure enough.
And it took a long time. It took like 40 years. LIGO was in development from like the 70s. Higgs boson, that was from the mid-60s to 2012. Bose-Einstein condensation. My advisor won a Nobel Prize for being the first to observe it, and he observed it in 1995, almost about a little less than 70 years after it was predicted by Bose and Einstein. It's insane.
But in science, laws stem from observation and experiment, not mathematics. Worse still, Kirchhoff's law has not stood the test of time.
Law is not a well-defined concept in the sciences. The things that are called laws are whatever. You know what? The best way of defining a law is, and I might get some pushback from other people. I don't know. A law is whatever everybody calls a law. Like honestly, if you hear a word that describes a model and that instantly sets all these preconceptions for you, you need to loosen up a bit, because guess what? Sometimes things are called things for historical reasons.
There's no valid theoretical proof of Kirchhoff's law, and there never has been. You can learn more about this problem in this lecture and in this paper, where Planck's derivation of the law is shown to be invalid. Next, what about Planck's law? What Planck did was provide a mathematical form for the blackbody radiation curve. Planck's equation is clearly accurate and yields the correct answer. However, because Planck believed that Kirchhoff's law was correct, his work remains incomplete.
Why is it accurate then? This is the Why is it accurate?
It is because of Kirchhoff's law that astronomers and physicists believe that they can obtain a blackbody spectrum from the universe without the need for a physical lattice. Kirchhoff's law has enabled astronomers to argue that...
Also because we know when we measure these systems, the law holds. That's why we think the law is accurate.
Stars or gaseous plasma devoid of lattice structure, and that black holes will be able to produce Hawking radiation through pair production. In addition, because of Kirchhoff, Planck himself believed that blackbody radiation was completely independent of the nature of the walls, despite the fact that he always had recourse to a carbon particle in his text on the subject, as was reviewed in this
I don't think that's a fair discussion of what Planck believed.
paper.
And this is the problem with people like this, is they will say things, and I don't even know whether or not to give it any credence at all. Because when he made the comment in the last video about how how Planck does differential measurements, and they've never released a direct absolute measurement, I was like, well, that might be true, that might be false. I have no idea, because I can't trust this guy, and I had to spend time to figure it out, and it was technically true, but for reasons which I would have been able to tell you 95% accurately before I even did the research, why? Because it's not designed to do the same thing.
As a result of all this, Planck's equation is the only expression in physics which has never been linked to a physical cause, as I discussed here.
And that is insane. That doesn't make any sense. Planck's law of radiation says that if you have a thing at thermal equilibrium, it's got some temperature, you're going to have photons being emitted from that. If it's a perfect absorber, photons are going to be emitted from that with a particular spectrum. How is that not a physical system that is being described? Is a photon part of a physical system, Maya?
I would go with yes. What is
Yeah.
I don't understand what his problem is, though.
So, at a high level, I think his problem is basically that the derivation uses a particular model in order to compute the density of states that is available to the system. And because that particular model is not always applicable, therefore the conclusions are not always applicable, even though all you need to have is have the density of states be sufficiently continuous, then because of energy conservation and photon number non-conservation, and this, you can derive Planck's law. You don't need to know exactly how each and every photon was produced. You just need to know the statistics. That's what statistical mechanics is about. Because.
No, yeah. Just put a period right there. Because.
Yeah.
It is true that the equation correctly gives a black body radiation formula. However, though Planck used oscillators in his derivation, he completely removed the need for a physical oscillator in accounting for the spectrum you see. If you believe in Kirchhoff's law, you do not require the oscillators. This has permitted astronomy to evolve without...
His point is that you need to have explicit thermalization. That is true. Everybody agrees with that. Nobody disputes that. It's just that part literally goes without saying in these contexts. It literally goes without saying.
Physical reality. Black body spectra could be produced with a pencil using theory alone, provided that the scientific paper, at least at some point, invoked thermal equilibrium. Yet, in order to obtain a black body spectrum in the laboratory, physics must have recourse to a nearly perfect absorber. Graphite and soot are often used. One would not build a black body from silver.
Yeah,
the reason is simple. You need a lattice that can both absorb and emit radiation in order to get a black body spectrum.
This is true. Not all objects are ideal black bodies. It has to be a perfect absorber for it to be an ideal black body. For something to be a black body, it has to be able to absorb any photon that you send into it. That's what makes a thing black, is it absorbs all the photons and it doesn't scatter any photons. If you take soot and you heat it up until it's glowing red, that is still a black body because it is not reflecting anything. It's emitting it, but it's not reflecting it. If it's hard for a photon to be absorbed, it's hard for a photon to be emitted because basically of time reversal symmetry. Or at least that's one heuristic that I think is pretty helpful.
The graphite and soot lattices meet this requirement, but silver does not.
Soot is not a lattice at scales larger than a few nanometers.
As polished silver is nearly perfectly reflecting in the infrared and
Doc,
microwave.
Care to
If you send any
wager a guess at this answer?
Oh man, so I haven't read the paper that came out a while back, and I didn't even watch all of Dr. Becky's video on it. But apparently there was a paper that thought basically that dark energy was tied to the mass of black holes. And when somebody explained the Cliff's Notes version of it to me at work, it made a lot of sense. Whether or not it's right, not my field. We don't know what dark energy is, though. That's like one of the real screwed up mysteries of physics and of cosmology. I think the first papers about it were published in like 1998 or something.
What it might be made up of, you mean?
No, that it was a thing, that you need to add this new term, basically, that the universe's expansion is accelerating.
Oh,
yeah.
Dark energy. Yeah,
Dark
it was
energy,
98.
yeah,
It was 98.
We don't know what dark matter is yet either, and that idea has been around for significantly longer. A little over twice as long now, I think. Maybe 3 times.
Google Fritz Zwicky. Here's the thing. It's like Max Planck died in, 1947. It kind of the guy at the very center of quantum physics.
He was the guy at the very beginning of quantum physics.
Yeah, I came up with a whole bunch of stuff that is responsible in large part for what we're doing today, or at least what we're able to do today. Seems like some of his ideas are pretty good, theoretically grounded, and hasn't gone wrong yet. So I don't understand.
I don't know.
Radiation into
What about the great attractor?
That's like a thing that apparently the entire like local area of the universe is like zooming towards. Mm-hmm. And I don't think we know what it, but maybe we do now. Maybe it's just a bunch of other galaxy clusters and stuff that we've been able to image. The great attractor is something that apparently like exists at like cosmological scales, like galactic superclusters and stuff. Things that are sizable, like noticeable fractions of the entire observable universe. That's what we're talking about, objects on like that scale. It's hard to do those, measurements. So yeah, funky.
So the secrets of the universe have not been unlocked, is what you're saying.
I mean, a lot of them have. We have like lasers and we have lasers and transistors. You have to understand a lot of funky things about the universe to have lasers and transistors work. You need to have like physics and then like a well-built classical physics, and then you need to go beyond that paradigm and completely replace it.
Oh, do you know what she's talking about here? She's looking for a name for something. No,
I
I'm sorry.
don't.
Are we making you think too much?
No, I'm just
The class has a lot of questions.
I'm not familiar with that. I wouldn't say that you can do it in like a proper tree where like you have one thing and then it branches off and the branches don't talk to each other. It would be all interleaving. The derivation of Planck's law that I have requires statistical mechanics, and it requires the solution of the Schrödinger equation in a three-dimensional box.
Immediately be transformed into blackbody radiation, as we saw in these videos. But if you do so in a silver cavity, or in a modern extremely reflective cavity using lasers, you will get standing waves if the incident radiation is phase coherent. The radiation will never become black, which is great, for otherwise lasers, MRI cavities, and cell phones would not work.
He's not wrong, but it's a straw man of I think what he thinks the argument like is. Anybody who says it doesn't matter what the walls are made out of for like any observable measurement, like no, that's dumb. It has to be able to be modeled as a thing that will absorb anything you throw into it. And a laser cavity, a high finesse laser cavity, is emphatically not that.
Perfectly reflecting cavities can never achieve thermal equilibrium through radiative processes, precisely because they are unable to absorb the incident radiation. They reach thermal equilibrium either through conduction or convection. The radiation which they contain remains completely dissociated from their actual temperature. That radiation remains a function of the radiation.
The main modes of the radiation, the modes that you're thinking about when you're thinking about a laser cavity, that's true. So what he's talking about here is, where's my marker? What he's talking about here is a similar thing to, so imagine that you have a string, right? And because a string is going to be a light wave. So light has a wave, right? And a string has a wave, and it's the same equation. If you have it fixed at this point and you have it fixed at this point, which are the two mirrors at the end of your cavity, then your light can only oscillate here, like that. It could oscillate like that. It could oscillate like that. But what you notice is that the ends are always fixed and you have an integer number of troughs and hills. That's what he's saying. But there's also just going to be like other random stuff floating around, and that is going to be due to the black body radiation. Like at least once you subtract out the bits that are from other effects, like multiple things can happen at once in a physical system. You can have a standing wave, and then you can also have radiation that isn't necessarily just in that mode. It just won't be confined to that mode, and when it hits the wall, it'll be absorbed. Maddening.
Perfectly reflecting cavities may or may not contain radiation, and that has absolutely...
They always contain radiation because they're always going to contain black body radiation. They're always going to contain that. They may not contain a non-zero quantity of photons in the allowed modes of the cavity, but that's a different thing.
Nothing to do with their temperatures. The perfectly reflecting cavity can reach temperatures...
Also, there's no such thing as a perfectly reflecting cavity, and that is not a minor point. It's...
equilibrium. But such cavities do not contain blackbody radiation unless that radiation was placed within it. As a result, Kirchhoff's...
It's placed within it by the things that are emitting things.
...law is false. Kirchhoff's law required temperature equilibrium, as you can learn through this English translation of Kirchhoff's work. The perfectly reflecting cavity easily meets this requirement. However, the radiation which it will contain will, in general, not be black. Of course, Kirchhoff was unable to study the perfect reflector using phase-coherent incident radiation. He lacked network analyzers and electronic test equipment. But if he had been able to study phase-coherent radiation and lasers, he would never have formulated a law stating that radiation contained within all opaque cavities must always be black and dependent only on temperature and frequency.
He would have added a very slight caveat that, as I said before, literally goes without saying.
While being independent of the nature of the walls at temperature equilibrium. So there is a lesson here, and the reason why I spent so much time on this channel treating Kirchhoff's law. Change in astrophysics is inherently linked to recognizing that Kirchhoff made an error. We need a distinct physical lattice to get a blackbody spectrum. An opaque enclosure is not enough, as our silver cavities with their standing waves prove. Of course, in 1862, Kirchhoff had no idea that silver cavities will someday be supporting standing waves.
I don't think he would have been that puzzled by that.
In any event, the lattice which seems to work best on Earth to produce a blackbody spectrum is the hexagonal planar lattice, which is found in graphite and soot. Such a lattice was never present in the Big Bang, and that is their problem. The Big Bang lacks a proper physical mechanism to produce the photons it claims.
He never makes this point. He never explains why you need a lattice for the photons.
Look, we've already been through this.
Creatures will not
Because
survive the passage of time.
it's like,
And
you know,
the
in cinema sense, and it's just like, why would they do that? It's like to make the movie happen.
Yeah, I know.
careful re-examination of the requirements for obtaining a blackbody spectrum. Someday, someone will link Planck's equation to the physical world. The physical setting required to produce a thermal spectrum will be recognized, and that setting will be the vibrational lattice. So when the need for lattice structure becomes recognized, big bangs, black holes, and gaseous stars will no longer survive. That will be the first real...
He doesn't think that stars are made out of plasma. I mean, he calls it gas, but he means plasma.
It means plasma, yeah.
Yeah.
explosion in
Wait,
physics.
he's not even using proper terms.
No, but honestly, that one doesn't bother me that much.
Why?
Because
He's supposed to have like actual training in this.
yeah, but I mean, people get loosey-goosey with the language. It just doesn't bother me that much when people say that the sun is made out of gas instead of a plasma, because like,
I mean,
a plasma is most plasmas are ionized gases, right? Like, I guess all of them, in some sense, are ionized
I don't
gases.
know what his. I mean, because like I think when most people think of a gas, they're thinking of something else, and I don't know what he thinks a gas is.
Well, he thinks so. To answer Peter's question, he thinks that stars are made out of liquid metallic hydrogen.
Oh, hey, Jason hit the nail on the head.
Yeah, it's really remarkable.
It will take
I
the
like
form
your
of
answer
cataclysmic
better.
change in physical theory.
Liquid metallic hydrogen.
And subscribe for more videos as we
No,
look
like
closely
stop the
at the
thing.
sun,
You're
the
not
stars,
doing
and
any of those things. Hit my like buttons.
I just subscribed to him. Oh wait, no, I
Why?
didn't.
Why would you do that? You're setting a very bad tone for the class.